We continue our discussion about functions. We go over a few examples, and we briefly talk about complexity analysis of algorithms. Just a quick recap, a function hides a complex chunk of code in a single named entity. So we assign a name, we call the function, we pass on input arguments, and we can get the result. So it allows a general method to be applied in varying situations. We can run it for different combinations of input parameters. We also talked about recursive functions, which are a function that call theirself. It has two parts encoding base case and recursive steps, and it can be computationally expensive. So we coded the Fibonacci sequence using recursive functions, and we saw that when we increase n, or the problem size, then the computational time increases accordingly. So overall, recursive functions can be computationally expensive. We also talked about higher order functions, which expect other functions as arguments and return functions as values. In particular, we talked about mapping function, which accepts a function and then applies that function to a list of values. Okay, let's go over a few review quizzes here. A recursive function usually runs faster than the equivalent loop, or usually runs more slowly than the equivalent loop. As we just discussed, recursive function can be computationally expensive, and the right answer here is option P. As you can see, it runs more slowly than the equivalent loop. The second review quiz, we have this expression, and want to know this expression evaluates to which options. So we are seeing map function over here, and a square root function under math, which calculates the square root of numbers. And then the second input argument is a list of numbers. So that function is going to be applied to all items. The square root of 9 is 3, the square root of 25 is 5, and the square root of 36 is 6. So as you can see here, the right answer is C. Now, the factorial of a positive number n, fact of n, is defined recursively as follows. So we want to write a code which calculates the factorial of a positive number using a recursive function. So if n is equal to 1, factorial of n is 1. Otherwise, it's n times factorial of n minus 1. So because we call the function with an updated input argument, it is a recursive one. Now, let's try to implement this in a notebook. So we define a function named fact, one input argument, one selection a statement, if n is equal to 1, colon, return 1, else, return n times fact of n minus 1. We run this function. In order to see some result, we need to pass on input arguments. Let's test 1. Fact of 1 should be equal to 1. Then we can try other input numbers, like fact of 3 equal to 6. We can calculate factorial of 10. So this was a simple recursive function with one selection a statement. Now, objectives for this lecture include using main functions. We want to learn how to implement main function, which automate the execution of different pieces of your algorithm. When you have several functions and you want to run them all together, we can use the main function. We also briefly talk about measuring the performance of an algorithm in terms of running time. There is a module in Python that we can use to measure the running time. Okay. So main serves as the entry point for a script. It allows the user to input different values and usually expect no argument. So it's the entry point, and we will be able to run several functions and different procedures altogether. Definition of main and other function can appear in no particular order in the script. So that's the important part. There is no particular order, as long as main is called at the end of the script. So in this example, you see two functions. The first one is main with no input argument. Number, we ask user to input a number, and its data structure is float. And then we call another function called a square, which calculates the square of that number. And then we use a print statement to show the result. After defining the main function, we define the square function, which we have seen before. One argument, and then it returns x times x. Now, the third part is the entry point for program execution. We need to add these two lines in order to make the main function work. If underline name equal to main. So these are special variables in Python, which execute all codes, all pieces of your algorithm. And then we call the main function. Let's try to implement this. First, we define the main function. Colon. Then we ask the user to input a number. So enter a number. And then we call another function, a square. We pass on number as the input argument to that function, and then we use a print statement to show the result. So the square of the number entered by the user is result. Now we can define this a square function, which needs one argument and return x times x. The third part, I'm going to add a comment, the entry point for program execution. If underline name equal to double underline main colon, and then we call the main function. Okay, let's run this. Okay. Enter a number. Let's go with 2. Name number, so there is a typo here. Fix this. Another typo. Now the square of 2 is 4. So you hit the run button once and then you run both functions together. We can try different numbers and then you can see the result. So here's another example that we are going to discuss in this lecture, approximating a square roots. So we know that there is a function under math module that calculates the square root of numbers. There is also an algorithm named Newton's algorithm for approximating the square root. So we want to implement that algorithm and then compare the result of the algorithm to that of Python's function, the square root function. So this function, the Newton's algorithm, so we want to define a function and that function expects the input number as an argument and returns the estimate of its square root. The script should also include a main function as an entry point that allows the user to compute the square roots of inputs until she passes the enter or return key. The steps are listed here. Okay. We first define a variable and initialize it. The variable is estimate and the initial value is 1. And then we see a while loop, while true, and we expect to see a break statement. So we update the value for estimate. So set estimate to the new value, which is given here, estimate plus x divided by estimate and then divided by 2. And then we calculate the difference. So we define another variable named difference, which is the absolute value of x minus estimate raised to 2. Now, if difference is less than the tolerance, so this is an iterative algorithm, and we define a tolerance, and we compare that difference. If it is equal or less than the tolerance, then we stop. So you see the break statement. Now let's try to implement this. At this point, I encourage you to pause the video and try to write the script and then compare your coding with what I'm going to discuss. Okay. First, I import the math module because I want to use the square root function. Then we initialize the tolerance. So I define a variable tolerance. It can be 0.001. It's arbitrary. It should be a small number. And then I define the Newton function with 1 argument. I'm going to add a couple of comments here. So this function returns the square root of x. It also performs the successive approximation. So I define the variable estimate, initial value equal to 1. Then we have the while true loop. We update estimate. And then we calculate the difference, which is the absolute value of x minus estimate raised to 2 and now I check if this difference is equal or less than the tolerance. If that's the case, break. Otherwise, go back to the top of the loop and eventually return estimate. Now I can define the main function. Add a comment here. So this function allows the user to obtain square roots. It must be indented. So we keep asking from the user. So we have another while true loop. They enter different values until they press the enter key. So while true, an input statement, enter a positive number or enter to quit. Now, if the value for X is empty, it means that the user hit the enter key, break. Otherwise, except X and its data structure is float. And now we want to show the result. So output the result using the print statement. The program's estimation is, we call the Newton function. We pass X as the input argument. And now we want to compare this value to that of a square root function under math module. Python's estimate is math.sqrt of X. Now we can add the entry point, these two lines. We run the main function. Okay. Now let's run this. Okay. Enter a positive number. Let's go with 2. So the program's estimate is 1.414 and the Python's estimate is given here, and you can see that they are pretty close. You can try another number, 10. You see the result, or we can press enter and then you quit the program. With that, let's answer this review quiz. Top-down design is a strategy that develops lower level functions before the functions that depend on those lower level functions, or it starts with the main function and develops the function on each successive level beneath the main function. So here the right answer is option B, because order doesn't matter, as it is implied in option B, in option A. So the right answer is option B here. The top-down design is start with the main function. With that, we wrap up chapter 6, our discussion about functions. And I would like to briefly talk about complexity analysis of algorithms, chapter 11 of our first textbook, Fundamentals of Python. The reason is that we can have different strategies to write algorithms. You can go with for loop or you can go with the recursive function. When choosing algorithms, we often have to settle for a space and time trade-off. It means that an algorithm can be designed to gain faster runtimes at the cost of using extra space or memory, or the other way around. So there is a trade-off. Now, memory is quite inexpensive for desktop computers, but again, it's one of the deciding factors. Now, one way to measure the time cost of an algorithm is to use computer's clock to obtain actual runtime. So there is a module in Python, time module, that helps you capture the computer's clock. So before you run the algorithm, you save the computer's clock, and then after the algorithm is run and finished, then you capture the time again, and the difference would be the running time for your algorithm. So it returns number of seconds that have elapsed between the current time on your computer. Here is an example. So we print the running times for problem sizes that double using a single loop. So we define a loop, then we double problem sizes, and for each problem size, we want to show the running time in seconds. So here we import the time module, one variable which represent the problem size, and then a for loop. We repeat this 5 times. First, we capture the time and we save it in the start variable. We go through the loop. So this is a very simple loop. It adds 1 to work and then subtract 1 from work. And then at the end of the algorithm, we can calculate the elapsed time, which is the difference between the current time and the start time. Now let's try to run this in Python, in the notebook. Okay. You can see I first import module. There's a for loop. We do it 5 times. We double the problem size at the end, and we show the problem size and the elapsed time, which is technically the running time. So let me run this. So for the first problem size, it's less than 1 second. When you double the numbers, then it's about 2 seconds. You can see that the running time is increasing. We are waiting for the last iteration, and now you can see it takes 14 seconds. So that's how we can measure the running time for algorithms. So this method permits accurate prediction of the running time of many algorithms. So you can compare algorithms based on the running time, but we should be careful. Different hardware platforms have different processing speeds. So the running time of an algorithm differs from machine to machine. So we need to report the operating system we are using, the computer specification, and the programming language as well. And sometimes it's just impractical to determine the running time for some algorithm with very large data sets. So we need to use other performance measures, which we are not going to discuss in this course. So a little bit about the complexity analysis. So you can plot the running time for your algorithms. So on x-axis here, you see the problem size. So you increase problem size, and on y-axis, you can show the running time. And then you can look at the behavior. So for example, here, the first algorithm behavior is linear, and the second algorithm is quadratic. So that's how you can plot the running time for different problem sizes, and it can be a measure for complexity of your algorithm. So technically, these two algorithms are different by their performance. And overall, we can have 4 orders of complexity. The best case scenario is the logarithmic one, which is even better than the linear one. We can also have quadratic, and the worst case scenario is exponential algorithms. So the computational time increases exponentially as you increase the problem size. And we have seen one algorithm which increases exponentially, and that's the Fibonacci sequence. So we use a recursive function for Fibonacci sequence, as you can see in this tree. It is an exponential algorithm. And that's why when we wanted to find Fibonacci of 100, we had to wait for a long time. With that, I want to go over a few problems, and I would encourage you to try to code these problems. And if you have any questions, we can discuss it in our live sessions. The first practice is to define a function which returns the position of the minimum item in a list. So it accepts a list as an input, and then we want to find the minimum value and return its position. The second problem, we want to return the position of the target item if found in a list. Otherwise, we return -1. So we want to write a function which accept a list sequence of items, and then we want to find the target value. So it's like a searching algorithm. And the last one, which is a very interesting question, how can we convert Fibonacci function to a linear algorithm? So we coded Fibonacci sequence using recursive function, and we know that its behavior is exponential. How can we change this and make it a linear algorithm? So in summary, in this lecture, we learned that different algorithms can be ranked according to the time and memory resources, and the running time of an algorithm can be measured empirically using the computer's clock